Hello, this is Professor Keen, and today I will be continuing my discussion of how it is that siphons work. And you might remember last time in this lecture, I had been talking about Chapter 16 of a student's Guide to the Great Physics texts, where I was discussing in a more general way how siphons work as Pascal described it. And so what I want to do this time is give a little bit more of a detailed calculation for how a siphon works. This is not exactly how Pascal does it, but nonetheless I think it's a helpful way to think about things. So what I'm going to do is I'm going to draw a problem, and then I'm going to work through it with you to show you how one can use the concept of the weight of fluids to show how a siphon works. So let's suppose we have a couple of buckets, one at a lower level than another. Okay, so here are two buckets, and then one right here. And I'm going to put a long glass tube sticking out of this one. And a long glass tube sticking out of this one as well. And these two glass tubes are going to be connected by another glass tube. You'll see why I'm doing this shortly. Okay. And moreover, there's a valve that I'm going to put right here. So this is a valve that we can shut or open in order to let water flow in one way or the other. And let's suppose that we, what we're going to do is, what order do I want to do this in? Let's suppose we have a fluid. It's an unknown fluid that is filling each of these tanks. But the density of this fluid, the density of the fluid is 4 times the density of water. Okay, so its specific gravity is 4. All right? And suppose we have that fluid in both of these buckets. And what I'm going to do is I'm going to imagine that we put this in an aquarium. So this is the bottom of the aquarium with this step on it. So we gently put this entire thing in an aquarium and we fill the aquarium with water. Okay, so, but we don't let the water go into these tubes. Instead, what happens is this water, the weight of the water is pressing down on the surface of this fluid and pushing it up into each of these tubes. So I'm going to draw the level of this fluid in each of these tubes. So the water, this unknown fluid gets forced up into this tube to some height. And also, it gets forced up into this tube to some height. And I'm drawing them at different heights because it will rise to different heights in those two tubes because there's different weights of water pushing on this side and on this side. You might see right away that the water over here, there's a larger weight of water pushing. So here you've got a larger height than over here, but nonetheless, this one is a little bit taller. Well, we're going to calculate these heights in a few minutes, so this will make more sense as we keep going. So I'm going to give you some measurements. Let's suppose you are told that, I'm going to move this over to here so it's out of the way. Let's suppose we are told that the surface of this fluid on the left-hand side is a depth of 80 centimeters or 800 millimeters below the surface of the water. Okay? And let's suppose we're also told, let's draw a line right here, and kind of at the center of this horizontal tube. Draw that line right here. And I'm going to extend this line right here, give these various heights. And this is the level of that fluid right there. So that's 80 centimeters over here from there to there. And let's suppose that the distance from here to here, that height, from the surface of the liquid there to the center of this tube, that is 10 centimeters or 100 millimeters, of course. And let's also suppose that the distance from the surface of the water in the right bucket to the center of the tube, that is 20 centimeters or 200 millimeters. And what we're going to be interested in finding is, first of all, we want to find the height of this unknown fluid over here. So we want to find the height on the right side. Tell you what, actually, why don't I label some things to make this a little bit easier? Let's call this point H right there. Let's call this point right here, so that's point H. This point here is point G. Let's call this point right here point F. Let's call this point right in here, let's call that point C. We'll call this point right here point B. We'll call this point right here, you'll see why I'm doing this in a minute also, point D. And we'll call this point up here point E. And this point up here point A. Okay, so in other words, the distance between A and B vertically is 80 centimeters. The distance between G and either B or C is 10 centimeters vertically. The distance between G and F is 20 centimeters. The difference between H and F is what we're trying to find. So this is the height right here of point H. Height of point H. Sorry, I'm using two H's there. Actually, let me use a little h there to make this a little easier to see. This is the height of point H. And let's draw a line over like this. So this right here is going to be the height of point E. And what we want to do is we want to find, first of all, the height of point E. And secondly, we want to find the height of point H. Okay. And third, we want to find the whether or not fluid, when we open the valve, moves to the right or to the left. So when we open the valve, does the mystery fluid, the red fluid, stay still or does it move? And if so, in which way? Okay, so let's see if we can figure this out. And by the way, we want to find the height of V. We also want to find the pressures at the various points. So maybe I'll say point 0. Let me go back. Maybe point 0 is we want to find the pressures at these various points. The pressures at each indicated letter. Put a question mark here, even though that's not a question. Okay, so first of all, 0. I'm going to get rid of that and that. Okay, so what is the pressure, first of all, up there at point A? Well, of course, we have all the atmosphere pressing down on that, but the air, we're not really interested in the air because the atmospheric pressure is going to really be small compared to the pressure that's exerted on this fluid by the water level. So we're just going to ignore the atmospheric pressure. We're just going to say that this is 0 atmospheres. That is just the ambient pressure of the atmosphere. Okay, or it's going to be 0, yeah, so 0. There we go. What about the pressure at point B? What is the pressure down here? Well, if the pressure was 0 up here, then the pressure down here is the pressure that's caused by 80 centimeters of water weighing on it. So we could calculate the pressure using pressure equals density times G times H to find the hydrostatic pressure. For this problem, it's actually going to be easier to just think about pressure in terms of a height of a column of water. So we could just say that the pressure at point B is the pressure exerted by an 80 centimeter column of water, or let's just say 800 millimeters of water. So down here, the pressure is caused by 800 millimeters of water resting upon it. So that's going to be the pressure at point B. What about the pressure at point C right here? Well, the pressure at point C is at the same height as at point B, but this one is inside the tube, this one is outside of the tube. So the pressure here and here is going to have to be the same. This is also going to be the pressure of 800 millimeters of water. Another way to think about this is this 800 millimeters of water has to have the same pressure as this column of this mystery fluid right here. So this fluid right here has to weigh the same amount as 800 millimeters of water. So we could call the pressure in here at that exact point 800 millimeters of water. Okay. By the way, that is going to give us a way of figuring out what the height of this is. After all, if this has the weight of 800 millimeters of water, and this fluid has 4 times the density of water, then we know right away HE is going to be, so this is the height at point E, oops, I'm using the wrong notation. The height of E is going to be 200 millimeters. This is the height of the mystery fluid. We know that because 200 millimeters of this has the same weight as 800 millimeters of water. So it would balance the 800 millimeters of water out here. Okay. What's the pressure at point D? The pressure up here. Well, we know that the distance between this level right here and this horizontal tube is 10 centimeters, right? So we know this is 10 centimeters. We also just found out that the height HE was 200 millimeters or 20 centimeters. So this tube right here there's 10 centimeters of this fluid above it and 10 centimeters below it. So if there was 200 millimeters of this mystery fluid going from here to here, then 100 millimeters of that mystery fluid is below that point and 100 millimeters is above that point. Okay, so that means that the pressure at this point is going to be half of the pressure difference between between E and C. So that means that the pressure at point D is going to be the same as the pressure of 400 millimeters of water, right? Because out here, that entire column weighs 800 millimeters of water. This weighs 800 millimeters of water. And so halfway up would be the weight of 400 millimeters of water. So there's 400 millimeters of water weight weighing down at point D. So the pressure at point D is 400 millimeters of water. Okay, I hope I haven't lost you so far. All right. I guess we've already answered that. The height at point E is 200 millimeters. Now, what is the height of point H? Well, I guess we're going to have to first find a few more pressures. So what is the pressure at, let's say, point F? What's the pressure down here? Well, that pressure is caused by this entire depth of water right there. We know that between this point and this point, there were 80 centimeters or 800 millimeters of water. And from looking at these two numbers here, we can see that this is another 10 centimeters of water. So from here to here are 90 centimeters or 900 millimeters of water. That means the pressure at point F is the pressure of 900 millimeters of water, right? Okay. Now, we can next find what the height of H is. We know that the height at point H, well, this height H is the height of this column of the mystery fluid. We know that that must weigh the same as 900 millimeters of water. So the height of H is determined by the fact that it must balance a 900 millimeter or 90 centimeter column of water. We also know that this has 4 times the density of water. So it is going to be 1/4 of 900 millimeters. And that is 225 millimeters. In other words, this column of mystery fluid is 225 millimeters high, so that when we multiply by 4, because it has 4 times the density, this has the weight of 900 millimeters of water. Okay. And what else are we going to want to figure out? Notice here, if this right here from this distance, H, is 225 millimeters, we know that this is 200 millimeters. So immediately we can find that this distance right here is going to be 25 millimeters or 2.5 centimeters. That is going to allow us to figure out the pressure at point G. The pressure at point G is going to be equal to a ratio of the pressure difference between H and F. So it's going to be 25 over 225, 25 over 225 of 900 millimeters of water. In other words, this is going to be, the pressure at point G is going to be 100 millimeters of water. That's probably the trickiest thing I've done so far. So how did I get that? Well, we know that between H and F, that has a weight of 900 millimeters of water, right? Because I had to balance all this water out here. So it's 900 millimeters of water. We also know that the pressure gets greater and greater as you move down here. So it has to, from a pressure of 0 up here to a pressure of 900 millimeters of water down there, it must increase gradually. So we're really asking how much it will have increased between H and G. It goes from 0 up to 25 over 225, because this whole thing is 225, that's 25 millimeters, 25 millimeters, 225 millimeters. So it's increasing by 25 225ths of 900 millimeters. So in other words, the pressure at point G was 100 millimeters of water, the pressure of 100 millimeters of water. Now, why is this relevant? We've just found the pressure at point G, so let me just highlight this. The pressure at point G is the pressure of 100 millimeters of water. What was the pressure at point D? Over here, the pressure at point D, well, we found that earlier, was 400 millimeters of water, the pressure of 400 millimeters of water. Okay, notice that the pressure at this point is higher than the pressure at this point. It's because you've got this much fluid resting on top of that point and a lesser amount of fluid resting on top of that point. So the pressure at this point is higher than the pressure at this point. As long as we have this valve closed, nothing happens. But as soon as we open this valve, you have a higher pressure here than here, and that pressure difference is going to drive the fluid flow in that direction. And that is precisely what's going to cause this siphoning action. You've got fluid over here that's being pressed down by this water. It's pushing the fluid that way and causing a pressure at that point to be the pressure of 400 millimeters of water. You've got all this water pressing down on the surface of this fluid, pushing it up here, but the pressure at that point is only 100 millimeters of water. So when you open the valve, this fluid flows in this direction, and you get the siphoning action as the fluid moves up here, around, and down here. So this is another way of thinking about how a siphon works. This is not a siphon caused by atmospheric pressure, but rather it's a siphon caused by the weight of water in an aquarium weighing down on this fluid. But all this stuff can transfer right over to understanding how siphons work in the atmosphere. So I will stop there.